Why does the universe have only one direction? What gives meaning to the arrow of time? Why does change never gather back? Is complete reversal ever physically attainable? The answer lies in a physical property that explains why change spreads in one direction: entropy. In this video, we will introduce a new physical understanding of the deeper direction underlying entropy, the common physical reality behind multiple scientific perspectives. Entropy appears through different scientific views, each revealing part of how the universe transforms. In thermodynamics, it describes the irreversible direction of change through heat flow and work. In statistical physics, it explains why distributed states become more probable than concentrated ones. In information theory, it explains why the original state of a system becomes harder to fully reconstruct once change has spread. A black hole provides a remarkable example of how entropy appears through these different scientific views. Thermodynamically, black holes possess temperature and entropy. Statistically, they correspond to enormous numbers of possible states. Informationally, they raise profound questions about whether the original information carried by matter can remain fundamentally recoverable once it falls into a black hole. Although different scientific views approach entropy through different domains and constraints, they all point toward the same underlying reality: irreversible change unfolding in one persistent direction. That persistent direction, and the physical background beneath it, is the central focus of this video. While entropy can be defined for a system, it also reflects how transformation extends beyond the system itself into the surrounding environment. And this is where its broader physical meaning begins to emerge. Entropy explains how change spreads from atoms to the structure of the universe. The more widely physical change spreads, the greater the entropy becomes. Physics describes the universe through equations that precisely capture physical phenomena and the measurable properties of reality. But fundamental equations by themselves do not impose a direction of time. They describe how states may evolve, not which way reality unfolds. Entropy provides the persistent physical direction through which the arrow of time becomes recognizable. When entropy is treated as a universal measure of physical change, a coherent pattern becomes visible. Without sufficient constraints, concentrated configurations evolve toward dispersion. Distributed states become more accessible than concentrated ones. As energy and matter spread across enormous numbers of possible pathways, a genuine transformation occurs in the structure of the system. Return remains mathematically possible, but physically unlikely, because the system is no longer what it was. A complete microscopic return would demand unbounded precision and work, making it physically unattainable. Here, the asymmetry we associate with time becomes physically evident. On the other hand, when sufficient constraints locally shape or compress a system, transformation continues through surrounding interactions, external work, and redistributed effects. This appears in processes such as the compression of gases or liquids, where local ordering can emerge only at the expense of greater dispersion elsewhere. The same direction appears across reality. Nature does not preserve concentration for free. Concentrated states require physical constraints and sustained work to be maintained, while dispersed states emerge naturally as those constraints relax. Through all these processes, the same persistent direction becomes visible, and this is the direction we recognize as the arrow of time. Entropy, in this sense, measures how physical change spreads. It is not a single isolated phenomenon, but a fundamental description of how physical transformations unfold. Motion, interaction, radiation, evolution, and even temporary stability are different expressions of entropy change within physical systems. The pattern changes form, but the direction persists. For this reason, entropy and its increase is tied to physical processes, not merely to heat transfer or temperature variation. Any physical operation that redistributes the effects of change, expands the set of accessible configurations, or enables interactions to propagate, carries an entropic cost. Machines operate because physical transformation continues to spread within the system and its surroundings. This is not an engineering flaw, but a physical boundary imposed by the nature of entropy. Entropy is not an abstract concept. It unfolds physically. This becomes visible even at the smallest physical scales. Let us begin with the atom, often imagined as a closed and orderly object. In reality, an atom is a dynamic environment filled with interactions, vibrations, and continuous exchange with its surroundings. An atomic state may appear localized and stable, yet a single interaction, one photon, one collision, one vibration, is sufficient for the effects of that change to leak into the surrounding environment. What could have remained a concentrated state within the atom becomes many distributed consequences outside it. Even within the atom, electrons do not follow fixed paths, making their interactions and possible effects distributed across regions rather than confined to a single trajectory. Entropy measures how widely the effects of change extend and spread. Nothing vanishes, change spreads. The same pattern appears in a cup of hot coffee. The transformation continues beyond the object itself. Heat flows from the coffee into the surrounding air, then into the room. Once it begins to cool, it never reheats itself. The system has transformed into a state in which the consequences of that change are distributed across a wider domain, making complete return physically unattainable. The pattern becomes clearer in the life of stars. Stars are vast thermal gravitational engines. Gravity acts as a powerful physical constraint, compressing matter in stellar cores, raising density and temperature, and enabling nuclear fusion. The released energy radiates into far colder space, spreading the consequences of that transformation across a wider cosmic domain. Temperature differences combined with gravity make work, light, and stellar evolution possible. Beyond individual stars, entire galaxies become vast arenas of transformation. The same physical direction scales upward into cosmic structure. Stars are born and die, matter is redistributed, radiation spreads, and structures persist only temporarily. What we observe as galactic history and evolution is a sequence of transformations shaped by the same direction, the spread of change from concentration toward broader dispersion. At the most extreme boundaries of gravity, black holes emerge. They are not merely gravitational objects, but extreme states of entropy. Any mass or energy falling into a black hole transitions into a fundamentally different physical state, where the consequences of that transformation continue spreading in an extreme physical form, reinforcing the same persistent direction of irreversible change. At the opposite limit lies absolute zero. It is not a reachable temperature, but a theoretical boundary where local physical transformation approaches its minimum possible state. As a system approaches absolute zero, thermal motion diminishes and the number of accessible microstates decreases. Yet approaching this limit requires progressively greater physical effort, as the remaining thermal effects must continue spreading into the surrounding environment, where any local reduction in entropy is accompanied by greater entropy elsewhere. The same pattern of transformation persists across atoms, stars, galaxies, and even black holes. The scale changes, the direction does not. Across every physical scale, the same principle persists. The more widely physical change spreads, the greater the entropy becomes. Time measures the duration and ordering of transformations, becoming recognizable through their unfolding and irreversible consequences, while entropy describes the persistent direction underlying that transformation itself. Physical change continues through interactions, surrounding effects, external work, and irreversible consequences, whether through unconstrained dispersion or through systems maintained under physical constraints. Every real change leaves consequences that cannot be fully gathered back, even if the microscopic laws are reversible. Complete reversibility, the full restoration of reality and of the original physical state, lies beyond physical reach.